Okay, I'm going to be explaining homework problem number 4-75 out of Shigley version 9 from my MAE 3323 students at OSU Tulsa. This problem, we have a pinned end for a beam, but that beam has this axial load member, an axial member on it, pinned here and pinned here, and then we have a true load of 100 pounds force, and the question is, what's the deflection of this system at point B? Now, this is a statically determinate problem, so we are going to do some statics to find out what some of the loads are. Then we'll proceed through with a strategy for solving the problem. Now, let's think about what energies actually show up in here. We're certainly going to have bending moments in here and bending moments in this region. Now, there is no bending moment in this region, okay? But if we want to know the deflection at point B, we're certainly going to put a dummy load pointing downward at point B. What we can't forget about is the axial load at C. And what we're going to do to handle this axial load is we're going to do the statics and figure out what the force is here, place a force at the end of the axial member, and then we will capture the energy stored due to axial tension in this axial member. This member stretching would cause the whole beam to slope down and would cause a deflection at B, and certainly the bending of this beam would cause a deflection at point B. What I think we're going to end up doing is we are going to solve statics here. We'll solve for the statics here because it's necessary to know the load there in each end of this axial member. We're probably going to let X move from right to left, and we'll be looking right as we write our moments for these two regions, but we'll probably then let X move from left to right in this region, and we'll probably be looking left. I think that's what the author did. We'll see that in just a moment. And we can certainly choose to look different directions as long as we cover the entire amount of material that's storing strain energy. It doesn't matter how we set up coordinate systems in each region. And so, scrolling on down, first of all, we are going to have a moment of inertia term, a BH cubed over 12 for the bar, and we're going to have a moment for that axial member, or sorry, an area for the axial member, which is a pi d squared over 4, so calculating moments of inertias and areas. You can see a free body diagram showing the reaction at the left-hand end, showing the reaction up above the axial member. And so we'll do our statics by, first of all, summing moments about point O right here, and that will include the reaction, the 100-pound load, and our dummy load Q. Then when we solve that moment for the unknown reaction at C, solving that equation, we will get a 3Q plus 183.3. I will leave it to you to check that moment equation. If you have any questions about it, ask about it in class. Then when we sum moments about point A, that'll let us solve for the reaction at point O. So summing moments about point A, set it equal to 0. It involves the reaction at O, and we can solve for the reaction at point O of 2Q plus 83.3. And now we'll talk about the kind of energies that are going to happen in this problem. We are going to have bending in the BD region. You can see the mouse right there. Okay. But the bending moment is going to be a Q times X kind of thing. Okay. And the partial would be an X quantity. But then we're going to set Q equal to 0 right away. And so the moment piece goes to 0, even though the partial doesn't. And so there will be no deflection term coming from this segment. That's what is explained right here. Bending in BD is only driven by Q times X, but when we set Q to 0, the whole moment goes to 0, therefore the whole integral term goes to 0 in region BD. In region A to D, we're going to write our moment by measuring X from the location of Q and looking toward the right. And so, I'm sorry, X is going to start at the place where the 100-pound load is. We can do what we want as long as we cover the material. So in this region, at location X, the moment due to the 100-pound load is 100 times X. The moment due to Q is Q times 7 plus X. And they're both the same sign. Author chose to call them negative. We'll go with that. So minus 100X minus Q times 7 plus X. The partial of that moment with respect to Q, that's the deflection we want, is the minus 7 plus X. And at this point, we can set that Q equal to 0. And in the region OA, Our moment is going to be the reaction at point O, written properly, of course, multiplying times x. And so the moment is the reaction at point O, which is 2Q plus 83.3. Pointing downward, therefore minus is what the author chose. We wouldn't have to. Multiplying by this new x, and the partial of that moment with respect to Q is a minus 2x, and then we can set this Q equal to 0 and simplify it, and we will in just a moment. The final energy piece will be the stretch in this axial tension member caused by RC acting here and RC acting there. And so our axial force is solved by statics earlier, was 3Q plus 183.3, and the partial of that axial load with respect to Q is 3. And again, we can set Q equal to 0. And so our total deflection at point B is the equivalent of the partials of U with respect to Q, but we're going to take our partials early and set Q equal to 0 earlier. And so this becomes FL over AE, partial of F with respect to Q, setting Q equal to 0. Now this was actually the integral of F over AE, the partial of F with respect to Q. But when we integrate over the entire length of that axial member, we're just going to get an L there, so we can actually just set this up without the integral and doing the integral. But then we have to integrate the 3 pieces that have moments, but actually only 2 pieces that have moments. And we've got a different moment and a different partial in each of the 2 regions. So plugging in the numbers for the axial tension piece, FL over AE, and then the partial of F with respect to Q was just a 3, so that's going to be sitting in there. And then 1 over E, which is a constant, EI, which is a constant, and we'll integrate in the 0 to 5 region and the 0 to 8 region. Looking back at the picture, this is our 0 to 5 region, and our, let's see, I said 0 to 8. That must be a 0 to 6 region, and there's nothing to do here because Q went to 0. And so 0 to 5, and that's a 0 to 6, not a 0 to 8. That was a little bit hard for me to see. And this is our M times the partial of M with respect to Q. And all of that in here. Let's see. M times the partial of M with respect to Q is here. And then in the region 0 to 6, we again have our M times the partial of M with respect to Q. The 1 over EI brought outside. We integrate over the region 0 to 5. We integrate over the region 0 to 6. This one has an x times x, that's an x squared term, will bring us an x cubed term. And this one has an x squared term, which will bring us to an x cubed term. And so it looks like the algebra that happened was to pull all of this stuff out of both of them, except for the x squared terms. Do the integration, plug in the numbers, I'll let you check all of that, and we get a deflection of 0.0155. Again, from a contribution of 3 terms, axial tension, moment in the region 0 to 5, moment in the region 0 to 6. And we have that deflection, and we use the dummy load Q. That ends this video.